While we've hopefully learned about the basics of electricity and magnetism by now, how do they work and function in tandem with each other? When it comes to electromagnetism, one of the most important equations to learn about is Faraday's law of induction, whose equation can be seen here. Before we take a look at how to use this equation in a sample problem, we first need to understand each part of this equation separately. At the most fundamental level, Faraday's law states that a changing magnetic flux can induce an EMF, or potential difference. The magnetic flux is defined as the integral of the dot product between the magnetic field and area vectors, where the area vector has a magnitude of the shape's area with a direction that's given by the right-hand rule, curling your right hand's fingers around the area loop with your thumb pointing in the vector A's direction. Essentially, the magnetic flux can be thought of as how many magnetic field lines are penetrating through a surface at any given time. However, the equation deals with the derivative of the magnetic flux with respect to time. In addition, being multiplied by n, or the number of coils of the area loop, what we're looking at here is essentially the rate at which the total magnetic flux changes. In other words, if the magnetic flux doesn't change, then no EMF or potential difference will be induced. One final, seemingly trivial thing to note is the negative sign in this equation. This negative sign actually describes a phenomenon known as Lenz's law. Lenz's law states that induced currents and voltages always create magnetic fields that oppose the original change, and we'll see how this works through a couple of example scenarios. First, let's take a qualitative look at how Faraday's law works. To do this, let's examine this loop of wire here and this bar magnet, where magnetic field lines point away from the North Pole and towards the South Pole. In this situation, there's three main ways to induce a potential difference which creates current in the loop of the wire. Most predictably, moving the magnet towards and away from the loop changes the magnetic flux felt. For example, if I were to move the north pole of the magnet closer from the right side of the loop, more and more field lines would penetrate the loop towards the leftwards direction, as the magnetic field gets stronger the closer the magnet is. As a result, due to this changing magnetic flux, an EMF will be produced. This EMF can drive a current around the loop, in a direction given by Lenz's law, or the direction which would oppose the increasing amount of leftward magnetic field lines. In other words, the current direction is that which produces magnetic field lines to the right, found through the right-hand rule. Another way to change the flux through the loop is to change the area of the loop itself. So in this situation, if the area of the loop were to gradually decrease, the induced current would try to make up or restore the field lines that used to penetrate the area, leading to a current in this direction here. Finally, because the magnetic flux involves a dot product between two vectors, changing the orientation of either the area or magnetic field will also induce a current in the loop. For example, if this loop were to begin rotating, the amount of field lines penetrating this exposed area would begin to decrease. This, like all previous situations, will induce a current that opposes the change in magnetic flux. When it comes to Faraday's laws questions, there can be countless different versions dealing with loops of wire, metal rails, or bar magnets that can come up on short answer problems. While they may each seem new and complicated at first, always make sure to work rigorously through Faraday's law to solve for different quantities like the induced EMF or current. Remembering the fundamental ideas that the induced EMF is proportional to the derivative of the magnetic flux with respect to time and opposes the change in magnetic flux direction, will simplify all of these problems into one hallmark equation, Faraday's law. With that, you can feel good that you've just finished learning about Faraday's law of induction.